For many modeling studies, determining an appropriate set of boundary conditions can be difficult. It is often the case that classical boundaries such as groundwater divides or rivers and lakes may be located at a great distance from the site of interest. In such cases, it is often convenient to first create a large regional scale model that extends to well-defined boundaries. After creating a regional model, a smaller local scale model that occupies a small area within the regional model is created. The solution from the regional model is used to define boundary conditions on the local model. Regional to local model conversion is often referred to as telescopic grid refinement. The main features of the regional model are shown in this figure. Most of the boundaries are no-flow boundaries corresponding to groundwater flow divides and bedrock outcroppings. A river runs through the left side of the model. There are 4 major production wells in the region. The region consists of an upper unconfined aquifer and a low confined aquifer. The imported project contains a 2-layer regional modflow model of the study site. The local site corresponds to a chemical plant with a small spill. Once the regional model is completed, a local scale model will be developed to analyze a number of injection or extraction well placement scenarios. These wells are part of a treatment system that is being designed. This slide outlines the process we will follow to create a local model. We will start by selecting the ModFlow Layers to Scatter Points command from the grid menu. In this dialog, we will choose the ModFlow data that we want to convert to scatter data. We have the option to include layer elevations, flow package data, recharge, and computed head values. We can also choose to subdivide the model layers. In our case, the local model will have 2 layers corresponding to the unconfined aquifer and 3 layers corresponding to the confined aquifer. We can see all of the data sets created from the ModFlow grid data by looking at our new scatter point set in the Project Explorer. Each category of data has been placed in a folder below the scatter point set. Next, we will create a new conceptual model for our local model with 1 coverage to define the model boundary. We will zoom into our local model area and create our model boundary. For this local model, we will place specified heads at opposite ends of the model and align the sides of the model parallel to the direction of flow. We will use a grid frame to create our new local grid. This will delete our existing grid and regional ModFlow simulation. Next, we will initialize our new ModFlow simulation. We need to turn on the recharge package and inactivate any cells outside of our local model area. We will apply our conceptual model to the grid by selecting the Map to ModFlow command. We are now ready to interpolate our regional model data to our local model grid. We will right-click on the scatter point set and select the Interpolate to ModFlow Layers command. This dialog allows us to choose datasets and interpolate to the ModFlow inputs. We can manually select scatter point datasets and map them to a particular ModFlow input. GMS will automatically match certain dataset names with specific ModFlow inputs. In our case, we want to interpolate layer elevations, starting heads, flow package data, and recharge. We are now ready to save and run our local model. We can see that our head contours match the regional model. We can also look at our model in side view and see that we have a 5-layer model. At this point, we could add wells to our local model to evaluate a cleanup scenario for the chemical plant. With GMS, it's easy to perform regional to local model conversions.